It's a pleasure to introduce James Cates, who literally writes the books on how hearing aids work. And he's going to be telling us about objective intelligibility and quality measures of hearing aid processed speech.
So I'm going to talk about intelligibility and quality metrics. And I will start by giving sort of an overview of how some metrics are designed, and then I'll come into some applications of those metrics to noisy speech, noise suppression, and hearing aids. And the examples and explanations are going to come from work that we've done in our lab at the University of Colorado in Boulder. This has been an ongoing project at CU Boulder, and we've had the assistance of graduate students, postdocs, and some external researchers. So I owe a lot of thanks to a lot of people who have helped create the data and helped me with the models. Carolina gave a short overview on some hearing aid processing. Since I'm an engineer, I'm going to take more of an engineering approach to this, which is what is going on inside the typical hearing aid. And the general design is a multi-channel filter bank with time-varying gain adjustments within each frequency band. Now, if we increase the gain in a hearing aid, that will improve the audibility of the speech. So that ought to improve speech intelligibility. But there's a downside, which is that if we are applying time-varying gain to a signal, we are generating amplitude modulation, we're introducing modulation sidebands, so we're creating nonlinear distortion. So from our point of view, there's an inherent trade-off in hearing aid signal processing, which is audibility against distortion. When we talk about intelligibility and quality metrics, to measure some of these effects, we want to measure the signal changes. And of course, we want to measure what we think are the important signal changes. And perhaps the most important are changes to the speech envelope in the multiple frequency bands. We want to determine the degree to which the envelope is modified. There are other aspects of the signal, the temporal fine structure, long-term spectral change that we may also be interested in measuring. We also want to develop a metric that can measure everything that is going on within the hearing aid. That is, we don't want something that is so thoroughly tied, say, to noise suppression that it cannot measure other aspects of hearing aid processing, such as frequency shifting. So we want to be able to measure the interaction of all the hearing aid processing that is going on. And we want to be able to do this in the context of a model of the auditory periphery and the hearing loss. That is, how has, in the impaired ear, how has the periphery shifted? Now, when we come to quantitative metrics, there are sort of two ways of designing them. Most common is an intrusive metric where the degraded signal, let's say the processed signal coming out of a hearing aid, is compared to a noise-free, distortion-free, reverberation-free reference signal. And we're going to compare these two signals, and in general, any difference, any change in a signal is considered detrimental to speech intelligibility or to speech quality. But when we say degradation and signal change, we have to include not only the effects of the signal processing, but how that processing interacts with the auditory threshold. So if speech sounds fall below threshold in the impaired ear and we are amplifying them above threshold, that may benefit our metric in the same way, hopefully that it benefits the hearing impaired listener. There are also a class of metrics, and this is becoming a hotter research area these days, that uses the hearing aid output, the degraded signal alone. And to implement a metric of this sort, you basically need to rebuild a machine model of auditory perception. That's not what I've been working on. What we've been doing are intrusive metrics. And I'm going to use the work that we've been doing in Boulder as examples of how a metric can be put together and how metrics can be used. And my work has been on the hearing aid speech perception index, HASPI, which is an intelligibility metric, and the hearing aid speech quality index, HASQI, which, as the name tells us, is a speech quality metric. So how do we build metrics? We want to measure what's going on in the signal, and we want to do so in the context of our understanding of the auditory periphery and maybe going higher up the brainstem. But in general, we're going to have a model of the auditory periphery. It may be simple as a filter bank, or it may be more complex. We're then going to extract aspects of the output of our model that we believe are related to speech intelligibility and or speech quality. So if we say we initially have a model of the periphery, this is somehow trying to infer what's happening in the cortex. And then we're going to relate our model outputs to human subject data so that we can get a mapping that says these changes that we can measure in the signal correspond to these changes in intelligibility or quality. That means the metric must be trained, i.e., we relate what we measure to some human subject data, which means that the metric is tied to the speech materials and signal processing used to train it. So if we train a metric on additive noise, that is the data that we measure in our laboratory that we get from our subjects is based on understanding speech in different kinds of noise or different signal to noise ratios, then there's no guarantee that metric will work for any other data. If you want something that is general that you can use to measure the characteristics of an unknown data set, an unknown or brand new form of signal processing, you need to train on a wide range of human subject outcomes. And we also have the effects of what we're trying to determine. If we're dealing with speech intelligibility, for example, and we are trying to predict complete sentences correct, that will give us a different mapping than if we're looking at individual keywords correct. And I'm thinking here of some test corpora like the IEEE sentences, where you have sentences and each sentence has 5 keywords, and the subject listens to the sentence through the processing that you're investigating and repeats it back. How many keywords did that person get correct? That's a different function than whether the person got complete sentences correct. And if I'm dealing, say, with speech quality, and I train my system on low data rate codecs, that's going to give me a different transformation than if I'm concentrating on additive noise. So again, just a reminder that if you want to apply one of these metrics to data that you have or to signal processing that you are developing, trying to extrapolate beyond the specific training data used for that metric may give you inaccurate results. So let's get a little bit more specific, and I'll explain the auditory model that we've been using for our HASPI and HASQI metrics. And the very beginning is a model of the auditory periphery. And so this is trying to build in a simple signal processing system some of the physiological effects that Carolina explained to you in her talk. I'm going to resample my signal. I want everything at a constant sampling rate just for consistency. There's the effects of the middle ear, the ossicles in the ear. We have an auditory filter bank to provide frequency analysis. We have mechanical motion mediated by the outer hair cells in the cochlea. And then we have the conversion of mechanical motion to neural firing that's mediated by the inner hair cells. And I'll show you some pictures as to what we've done. The middle ear filter is a bandpass filter. It has a high pass section here with a cutoff of about 350 hertz. And we have the low pass section here with a cutoff of about 5 kilohertz. The actual middle ear filter is extremely complex. We have the ossicles, we have ligaments controlling the ossicles, we have muscles that are affecting the ligaments, and so on. This is a very simple model that gives us a good first order approximation. Auditory filters, with increasing hearing loss, the auditory filters get broader. So not only do we have a threshold shift associated with hearing loss, we also have reduced frequency resolution in the auditory frequency analysis. For small amounts of loss, we have an approximate linear dependency as shown by this red dashed line. As the loss due to outer hair cell damage increases beyond about 25 dB, what we see is a substantial rise, a substantial increase in the auditory filter bandwidth. What signal intensity also impacts the auditory filters. And this is based on some human perceptual data that Stuart Rosen published many years ago. So for very low signal levels, the bandwidth stays relatively constant. So for dealing with normal hearing, that would be a normal bandwidth. Then as the signal level increases, the bandwidth of the auditory filters increases till at very high levels, the filters are the broadest they can possibly be. If we started with a damaged ear, we would start with somewhat broadened filters, depending on the amount of hearing loss we have. And then at about 50 dB SPL in the model that we're using, the bandwidth would then start to increase till when you get to 90 to 100 dB SPL inputs, you are again at the broadest possible bandwidth. What about the filters? There are many ways to model auditory filters. A very popular one, a relatively simple one, is known as a gamma tone filter bank. And this is trying to approximate the auditory filters, the tuning curves in the cochlea. The filters are very sharp at high frequencies. They are broader at low frequencies. The filter slopes are steeper on the high frequency side than they are on the low frequency side. When we model impaired hearing, we make the filters broader, and we also change the filter shape. So if we just look at, say, this highest one, and in our system, that's a filter with a center frequency at 8 kilohertz, we can see how much broader that filter gets with the maximum amount of hearing damage that we can represent. But we also change the filter shape so that the ability of the auditory filter to reject intense low frequency sounds in the impaired ear is greatly reduced compared to the healthy ear. And we've tried to reproduce that in the peripheral model that we're using. And we also have the fact that the outer hair cells mechanically modify the signal intensity. For low input levels, we have essentially a linear system, and similarly for high input levels, 90 to 100 dB SPL, I'm using 100 here, the system is linear. But in the middle, the outer hair cells provide dynamic range compression. So the healthy ear is controlling the dynamic range of the signal. As we increase the amount of outer hair cell damage in the real ear and in the model, what happens is that the linear portion gets shifted. So we're now bringing in a shift in auditory threshold down here. The high intensity behavior stays pretty much the same because the outer hair cells aren't doing very much of anything. But the region of dynamic range compression is therefore reduced. We have a lower compression region, lower compression ratio, and a narrower region over which compression occurs. So when we have the maximum amount of damage, the ear becomes essentially a linear amplifier. So in talking about hearing loss, there's a term called recruitment, which is unusually rapid growth of loudness. And that's represented here by the straight line. As the signal increases, there's no compression to control that increase. It happens as fast as it can. And with the inner hair cells, we're now converting mechanical motion into neural firing spikes. The dominant effect here is that when a sound starts at the very onset of a sound, we get a lot of neural firing, and then the firing rate slows down as that sound continues. So here I have a sinusoid, I've turned it on, and then I've turned it off, and we can see that as soon as I turn it off, we have a peak in the neural firing, and then that firing rate slows down and remains constant at a lower level. So the auditory system is sensitive to changes, especially onsets of sounds. And if something stays the same for a while, we get bored and we reduce the firing rate. So again, this may be important for building some models of speech and speech detection because onsets seem to be more important than steady state. So to summarize the auditory model, we are using the same peripheral model for intelligibility and for quality, and we have built a model that we can degrade, that we can break gracefully to represent normal into impaired hearing and into moderate to severe hearing losses. We can, in our system, the hearing loss is based on the audiogram. We know there are individual differences in hearing, but the basic model is more of an average across listeners with similar audiograms than it is individual idiosyncrasies in hearing loss and acoustic processing. And that model has elevated auditory threshold, increased auditory filter bandwidth, reduced outer hair cell dynamic range compression, and that leads to reduced amounts of two-tone suppression. Two-tone suppression is an effect where a tone outside the passband of an auditory filter can reduce the gain within the passband of the filter. And this is tied into, I think, some of the tip to tail differences in the impaired filters where the low frequency gain is much, much higher than the low frequency gain in auditory filters in a healthy cochlea. Our model produces two outputs. One is a modulated envelope in each band expressed in dB auditory threshold. And we also have a term that we call basilar membrane vibration, which is not just the envelope, but the output of each auditory filter. So that's envelope with the carrier. And so that includes the temporal fine structure within each band. Well, how do we, that is just the auditory front end. What do we think are important in determining intelligibility and speech quality? So HASPI version 2, and this is a paper that came out just recently. By the way, I have a list of references at the very end, so I'll display that as the last slide. So we are comparing, say, the output of a hearing aid to a reference signal. For intelligibility, our gold standard is the way the normal hearing periphery would process that speech signal. So our reference is clean speech going through a normal hearing periphery, whereas the process signal is, say, the output of a hearing aid as perceived by someone with an impaired periphery. So we're starting with the outputs, with the envelope outputs produced by the auditory peripheral model. We're not particularly interested in silences, so we'll prune our signals to get rid of the silences. We're then going to look at time frequency analysis. So instead of just looking at the envelope within each frequency band, we're trying to describe the shape of the short-term spectrum as the short-term spectra progress in time. And to describe the shape, we're going to use half cosine basis functions going from 1/2 of a cosine fit to the entire spectrum to 2.5 cycles fit to the entire spectrum. Those of you who might have done some work in speech processing, speech recognition, will recognize this as Mel frequency Kestrel coefficients, because we're starting with the log spectrum in dB on an auditory frequency scale. And I'll show you a picture in the next slide as to what these functions look like. Each coefficient sequence, then we have 5 of these, is passed through a modulation filter bank. And we're going from 2 hertz up to 256 hertz. So we're looking at what is traditionally considered the speech envelope, all the way up into pitch periodicity. So we have 5 basis functions. Each one of those sequences goes through 10 modulation filters. So we have 10 sequences. So we're like 50 sequences rather. So we're building up a lot of data. We cross-correlate each of these sequences, the hearing aid output in the impaired model versus the clean speech in the normal ear model. Then we average over the basis functions, and we end up with 10 correlation values for the modulation, the envelope modulation rates. These are the basis functions that we are using. If we look at basis function number 2, that represents spectral tilt. If, say, we have a vowel with a lot of energy at low frequencies, very little energy at high frequencies, we'll have a large positive value here. If we're looking at the onset of, say, a burst or a stop consonant, we may have a lot of energy at high frequencies, very little energy at low frequencies, and that would give us a large negative value. So as we observe this over time, it's going to be flipping back and forth, positive, negative, and that gives us an idea of how the spectral tilt is changing as a function of time. Now, to map the output of our cross correlations into subject data, we're using a neural network approach. So we're looking at entire sentences correct. Remember, I said there might be differences if you're looking at the number of keywords correct. So this work that we done is tied into complete sentences correct. We've looked at a lot of different conditions, including noise, multi-talk or babble, the impact of noise suppression, wide dynamic range compression, frequency shifting. That's part of a lot of hearing aids. We've also looked at the impact of reverberation and processing to try to ameliorate the effects of reverberation. We're using a relatively simple neural network. So the input layer is the 10 average modulation rates. There's a single hidden layer with just 4 neurons. There's one output layer and a sigmoid activation function. But even such a simple neural network has a lot of free variables. There are about 44 variables in this. So it's really, really easy to build something that overfits the data. That is, it does such a good job with all of these degrees of freedom available that it represents a specific data set rather than being generalized to across all data, including data you haven't seen yet. So to help with the overfitting, we're using something called bootstrap aggregation, also called bagging, where we build 10 networks, each fit to a different random selection of the data we're trying to fit and our model outputs, and we average over the 10 networks. Okay, what about quality? Well, quality, I think, is a little bit different than intelligibility, and the quality model is going to be different from an intelligibility model. We've done a lot of our work using just a pair of sentences, so there's possibility of some sample bias here, but we've used one male and one female talker. We've looked at noise, multi-talker babble, linear amplification with resonance peaks, and various kinds of nonlinear hearing aid processing. There's a nonlinear term, and there's also a linear term. The nonlinear term looks at envelope modulation and at temporal fine structure changes. The linear term, which is based on some work that Brian Moore and Chin-Chuan Tan did quite a few years ago now, looks at differences in the long-term spectrum and slope. So with intelligibility, we were using an envelope modulation filter bank. For quality, we're using a simpler approach. We're just low-pass filtering the envelope modulation. So we're using a sliding 16 millisecond window. So that gives us a low-pass filter. Again, we remove the silences, and then the remaining segments we fit with the same half cosine basis functions, those middle frequency Kepler coefficients that we use for the intelligibility metric. And again, we look at how those change over time, and we cross-correlate changes over time for the process signal with changes over time for the clean reference signal. And we then average over basis functions 2 through 6, half a cycle per spectrum to 2.5 cycles per spectrum. And that gives a value denoted as C. We then also look at some changes in vibration, look at changes in the temporal fine structure. And we put this in because for speech quality, we know that if I build something like a noise vocoder, I can get nearly perfect intelligibility, but the quality is still going to be very low because the temporal fine structure, the pitch periodicity effects, for example, have been thoroughly corrupted by the noise vocoder. So we're looking at the basilar membrane vibration. So that's the filter outputs and not just the envelope of the filter outputs in our Cochlear model. Again, you're looking at 16 millisecond segments. And what we're going to do is cross-correlate each segment in the hearing aid output with the corresponding segment in the clean reference signal at the hearing aid input if we're just looking at hearing aid processing alone, no noise. The inner hair cell firing tracks pitch periodicity at very low frequencies, but it loses that ability to respond at higher frequencies. So we're modeling that with a low pass filter, and then we sum across time and we sum across filter bands, and that gives us the vibration correlation term denoted by V. And our nonlinear model is C squared times V. This is a completely empirical fit. There is no theoretical justification for it, other than it seemed to do a really nice job representing human subject data. There's also a linear term where we look at the RMS average envelopes in each of the frequency bands for the reference going through a model of the impaired periphery and for the hearing aid output signal going through a model of the impaired periphery. And we sum these values, and then we look at the standard deviation. So if I have the long-term spectrum for my sentence for the reference signal, I have that spectrum. I then have the long-term spectrum at the output of the hearing aid that's then gone through the model of the impaired ear for the hearing aid processed signal. I can then look at the differences between those two signals and compute the standard deviation. I then take the first difference across the spectra, so the band K minus band K minus 1, and do that for the reference and for the process signals, take the standard deviation of those differences, and our model of linear effects, the linear changes in the signal, is 1 minus a weighted combination of those two standard deviations. The entire model is then the product of the two. Envelope is most important for nonlinear changes, but temporal fine structure plays a role. Linear term spectrum and spectral slope changes are also both important. And because it's a product, we can see clearly that a change in either linear or nonlinear parts of the signal will reduce quality. And if we look at intelligibility predicted and quality predicted as a function of signal to noise ratio for long-term average speech spectrum shaped noise, we can see that intelligibility changes very rapidly. From -10 to 10 dB SNR, we go from no intelligibility to perfect intelligibility, whereas the quality changes much more gradually. And even at a 40 dB signal to noise ratio, our model and the human subject data on which it's based say that there is still some loss in quality, even under conditions where it's very hard to detect, but not impossible to detect the presence of the noise. Now, some applications. How have we been able to use this, and how can other people use metrics like these? Okay, one application that we've looked at is quality ratings for noisy speech. And this is a paper that came out last year. So we want to look at the relationship between subject listener quality ratings and the envelope modulation inherent in the noise and in the speech. So we looked at 10 older adult hearing impaired listeners. We looked at 5 different types of noise: multi-talk or babble, a conversation, street noise, kitchen recording, and a fast food restaurant. Different segments, randomly selected different segments for each of these different noise types for signal to noise ratio. So pretty big experiment. And we used a bilateral hearing aid simulation. We didn't use real hearing aids here. We used them programmed in MATLAB, and we got quality ratings for a male plus a female sentence pair. So to give you an idea of how different types of noise vary, here is the envelope over time for the babble that we used. Here's the envelope over time for the kitchen noise. We can see that the babble is much more stationary than the kitchen. If we look at the subject ratings, here on the left panel, we have signal to as a function of signal to noise ratio for the different kinds of noise. We can see that the subject ratings, well, first, as we reduce the amount of noise, as we increase SNR, the ratings get better. I mean, if that didn't happen, we don't have a paper. But we also have the fact that for the kitchen noise, at the same SNR as for the babble, the kitchen noise gives us much higher ratings than the babble. And we believe this is due to the more intermittent nature of the kitchen noise, where you have a low average level, but you have sharp spikes in the intensity. On the right-hand side here, what we have is the capsule correlation. So that's the envelope variation term in our quality model. And we can plot that as a function of SNR. And we can see that the general shape of the noise for each of the types of noise that we use agrees very nicely with the subject ratings. All of the ratings, all of the calculated values for the kitchen noise are the highest, as they were for the subjects, and the babble is quite low, not necessarily the lowest, but still quite low, and that also agrees with the subject. So when we cross-correlate Pearson here, the R squared, we have the capsule correlation along the x-axis, the subject ratings along the y-axis. So we have a very, very good degree of correlation between that nonlinear distortion term that we're using in our model, in our metric, and the actual subject ratings. So if R squared is 0.92, then the Pearson correlation coefficient is about 0.96. They're doing quite nicely. Whereas if we just plot things as might be traditionally done as a function of SNR, SNR doesn't take into account the different temporal properties of the different types of noise at the same SNR. So we have much more spread at each of our signal to noise ratios and a much lower degree of correlation. So this suggests that some of the way of looking at envelope as important in describing speech and noise is a very useful way of doing it. What about noise suppression? I mean, that's a very important aspect of the Clarity workshop. And I took a look at noise suppression algorithms a few years ago, and I compared several different noise suppression, single microphone noise suppression algorithms: spectral subtraction that incorporated an upward spread of masking term, ideal binary mask, and restoring the envelope of the noisy speech to exactly match the envelope of the clean speech. So we also compared noise estimation procedures that in the ideal binary mask, for example, you assume you have the speech and noise as separate files. And for every time frequency cell in your processing, you assume that you can do that you know exactly what the noise power is and exactly what the speech power is, and you can decide what gain you want to apply to that cell. But in the real world, we don't have that kind of ideal knowledge. The best we can possibly hope for is a good estimate of the average noise power. We don't know the fluctuations in detail over time, especially not when speech is also present. So, and we looked at normal hearing and a moderate flat loss audiogram and averaged over several sentences. So spectral subtraction, the Wiener filter, is here. We also looked at power spectral subtraction and magnitude spectral subtraction. Also, many years ago, there was a few papers that suggested that if instead of having this steep drop off at low SNRs, if you smooth the curve a little bit, you might get better results. So I tossed that in as well. If we look here on the left panel, this is the predicted intelligibility as a function of SNR. This solid black curve is if we don't do any processing at all. So that's the worst case. The upper curve is if we have ideal knowledge of the speech power in every time frequency cell, the noise power in every time frequency cell. We use that to compute the instantaneous frequency time dependent SNR. We can see that we get very good improvement in intelligibility. At really good SNRs, the processing isn't doing very much. At poor SNRs, it's turning the noise into noise that's been modulated to look exactly like the speech, i.e. a noise vocoder. Our interfering noise here is multi-talk or babble, so it's not quite a noise vocoder, but we do get the expected good intelligibility performance. And the Wiener filter does quite well. Some of the other processing approaches not so well. And we see very similar behavior for the quality prediction when we look at it as a function of SNR. Again, without any processing, we have very poor behavior. When we have ideal envelope restoration, we get much better predicted quality. The Wiener filter is very close to what the ideal restoration would do. The ideal binary mask has asymptotes at relatively low quality because the ideal binary mask is setting a gain of 1 or 0, nothing in between. If you want to keep that time frequency cell that has a positive SNR, 0 if you don't want to keep it, that time frequency cell has a negative SNR. So we have lots and lots of gain changes, instantaneous gain changes or nearly instantaneous changes, and that generates lots of modulation sidebands, lots of spectral splatter. Well, what happens if we just have the average? Well, what we can see is that the average, if we base our spectral subtraction on the noisy speech power compared to the average rather than instantaneous noise power, the processing does very little. Our prediction is that there's essentially no benefit at all, no matter what algorithm you use, if you don't know the instantaneous noise power. And that applies to intelligibility here on my left side and quality here on the right. We've also been able to look at real hearing aids, not just processing simulations. And we looked at, can the metrics, can intelligibility and quality metrics actually distinguish between hearing aids? So we're not looking at which one's the better fit or which one's a poorer fit or which one benefits the end user the most. We're looking at a simpler question, which is, can we even tell the difference? Can the metrics show us that these two devices are different devices and not the same? Again, our favorite pair of sentences. We looked at hearing aids from 3 manufacturers, basic and premium models from each, and we looked at wide dynamic range compression, noise suppression, and frequency lowering. And we set up the hearing aids to either give us just linear processing, mild processing, which had no noise suppression or frequency lowering, moderate, which sort of agrees with the way you would set up the hearing aid if you followed the manufacturer's recommendations for the audiogram, and then max, when we try to goose things to get as much signal distortion as possible. We looked at a mild sloping loss and a moderate to severe flat loss, and we varied the signal to noise ratio and level of presentation. For our measurements, we used a B-in-case acoustic test box that we placed in the sound booth in our lab to get as much sound isolation as possible. It still wasn't enough. Here we can look at, for example, signal to noise ratio. And as we increase the signal level, we can see that for speech and noise, increasing the signal level of the noisy speech gives very little benefit, because no matter how much you amplify the speech, you're amplifying the noise along with it, and the signal to noise ratio is unfavorable. So you can't extract the speech from the noise. In quiet, however, amplification does help, because now you're amplifying the speech and perhaps some of those low intensity portions of the speech above the impaired auditory threshold. And you can now see that there is some additional benefit to amplification. So this reinforces the statement that we heard earlier, that speech in noise is a big problem. And if we look at quality, however, as we increase the signal level, the quality goes down. And here our best guess is that as we increase the signal level, we are getting distortion components generated by the hearing aid. We're amplifying those above the impaired threshold. We can hear more of them, and we complain. What about the processing? As we increase the aggressiveness of the hearing aid processing, if we look here at our quality prediction in quiet, what we can see is that as we make the processing more aggressive, the quality goes down, both for the sloping loss and for the flat loss. So again, we can see that this trade-off between amplification and nonlinear distortion is something that we can measure, and we believe this is important in hearing aid processing. So in conclusion, we think that intelligibility and quality metrics can accurately predict listener responses. What we've done is to use the same peripheral model for both normal and impaired hearing, the same peripheral model for intelligibility as for quality, and we can measure changes in the signal due to nonlinear distortion, due to additive noise, due to linear response modifications, as well as the nonlinear response algorithm effects. Envelope fidelity appears to be very important, but we want to be able, and we can measure what's happening in the complete system. We treat the hearing aid as a black box. We compare the output to an ideal input. And as I've mentioned, there seems to be this trade-off between audibility and nonlinear distortion, and we want to be able to measure that. Limitations of what we've done in our lab. First of all, we've derived things for monaural headphone listening only. We're now gearing up for a binaural experiment, but we don't have any data yet. We've been using sentence test material. So if you're interested, say, in keywords correct, or if you're interested in phonemes correct, or that kind of an analysis, or if you're interested in connected discourse, or paragraph long effect, these models may not give you accurate enough results. And I've gotten requests for the code from people in China and other people, other nations, where tonal languages are used, and these models are not validated for tonal languages. I would not believe any predictions made by almost any of the existent intelligibility and quality metrics for tonal speech. And if you're interested and want to take a look at the code, or would like to use it, or you want to be able to break it, that's great too. Send me an email and I'll send you the code. And here we have the references. So that's it. Thank you.